AI philosophy, enabling humans to establish destiny for themselves and establish a mind for AI. Unlike the frequentist school, which views model parameters as unknown constants, the Bayesian school regards model parameters as unknown variables that themselves follow a distribution. Therefore, it typically assumes that the parameters follow a prior distribution and then uses observed data to revise the posterior distribution of the parameters. This iterative process of revision also allows the scientific principle of falsifiability to be seen as a Bayesian methodology. The Bayesian school believes that all probabilities are subjective and that there is no such thing as an absolutely objective probability. In contrast, the frequentist school considers model parameters to be objective and views prior distributions as a form of bias that is difficult to obtain and overly subjective. Click the plus sign to follow this account for more exciting content. Unlike the frequentist school, the Bayesian school treats model parameters as random variables, quantifying parameter uncertainty by introducing a prior distribution. Specifically, the Bayesian school views model parameters as unknown variables that themselves have a distribution. Therefore, it usually first assumes the parameters follow a prior distribution. Choosing different priors may affect the results, and then uses observed data to compute the posterior distribution of the parameters. The Bayesian school, centered on Bayes' theorem, as shown in the figure below, posits that probability is a subjective measure of uncertainty, that is, the degree of belief in a proposition or hypothesis. Key methods of the Bayesian school include probabilistic graphical models, naive Bayes classifiers, Bayesian networks, and Markov-Chain Monte Carlo (MCMC) methods. These are applied in scenarios such as spam filtering based on word frequency priors, real-time risk prediction systems, e.g., financial fraud detection, and recommendation systems. The Bayesian school believes that intelligent behavior is not only reflected in fitting data, but also, and more importantly, in modeling and reasoning under uncertainty. The Bayesian school treats probability as a degree of belief using a prior distribution based on existing knowledge or experience and new observational data, the likelihood function, to update the belief about unknown parameters, resulting in the posterior distribution. It views learning as a dynamic process. As new data continuously arrives, the prior probability is updated to a posterior probability, which is then used for prediction and decision-making. For details, refer to section 13.9, 1 prior probability, likelihood function, posterior probability, and Bayes formula. The advantage of the Bayesian school lies in its powerful capability for modeling uncertainty, handling issues like small samples, high-dimensional data, and missing data, making it particularly suitable for scenarios requiring dynamic knowledge updates. Notably, it can generate quantitative descriptions of uncertainty, which is especially important for decision support systems. However, it also faces challenges such as high computational complexity and difficulty in selecting appropriate prior distributions. To overcome these limitations, researchers are continuously exploring new approximate inference methods, such as variational inference and expectation propagation, and strategies for designing priors, significantly enhancing the practicality of Bayesian methods in deep learning, e.g., Bayesian neural networks, and medical diagnosis. The Bayesian school introduces probabilistic methods into artificial intelligence, simulating inference and decision-making based on probabilistic measures. Unlike the frequentist school, which views model parameters as unknown constants, the Bayesian school views model parameters as unknown variables that themselves have a distribution. Therefore, it typically assumes the parameters follow a prior distribution, then uses observed data to compute the posterior distribution of the parameters, and solves for the parameter data using methods like maximum a posteriori, MAP, estimation expanded via Bayes formula. The Bayesian school believes that all probabilities are subjective, requiring a subjective determination of the parameter's prior distribution, i.e. theta, thus viewing parameters as variables with a probability distribution, and holds that no objectively existing probability exists. The following introduces the differences between the Bayesian and frequentist schools. More details can be found in section 13.9. 4. The debate between the Bayesian and frequentist schools. The Bayesian school believes all probabilities are subjective, therefore requiring manually specified the prior distribution of parameters. They view parameters as variables with probability distributions, asserting that there is no absolutely objective probability. The frequentist school, on the other hand, considers model parameters to be objective, viewing prior distributions as a form of bias, and trusting only the observed objective data. Consequently, the frequentist school often criticizes the Bayesian school's prior distributions, arguing they are difficult to obtain and overly subjective. The Bayesian school counters that prior distributions originate from an individual's past experience and hold significant meaning themselves. They argue that the exact accuracy of the prior distribution is not critically important because one can first make an assumption about the prior. When the actual situation conflicts with the prior knowledge, for example, if the posterior probability estimated from newly collected data deviates significantly from the prior probability, can cast doubt on the current belief parameter prior and lead to a revision of the prior knowledge. This iterative process of revision allows the scientific principle of falsifiability to also be seen as a manifestation of Bayesian methodology. I am Wu Huaiyu, a PhD from the Chinese Academy of Sciences and a postdoctoral fellow from Peking University and the founder of AI philosophy. For more detailed information, please refer to the complete version of this book. In addition to this short video, you can also click on my avatar to view more long videos.